Hello, class. Welcome back. This is lecture 19. Today we're talking about systems of differential equations. That's right. You can have systems of differential equations just like you can have systems of linear equations that you studied a long time ago. And so we're going to look at these next, but only the ones we can do. There's a lot more to say about them than what we're doing, but that's okay. We're just going to use them to model some situations. And then we'll solve those ones with the Laplace transform, but there's lots of other things we could do, like I said. Okay, so the idea is there's more than one variable changing. And so systems of differential equations help us deal with these sometimes. So here's the first example, which we're not going to solve. I just want to mention because I think it's cool. This is called the predator-prey model. So it has to do with population growth. So the idea is, suppose that you have an ecosystem, let's say rabbits, that has rabbits in it. They just can eat as much as they want. And so y of t will be the number of rabbits at time t. And previously, you might say how fast they grow. Previously, how about before? So before, we might have said that dy dt was proportional to the number of rabbits currently there. So we would write something like this. So population grows proportionally to the current amount. More rabbits later. That's the idea. But what we're doing now is we're going to introduce a second population that eats rabbits. So now suppose there are about wolves, those eat rabbits, I think. Wolves that eat rabbits. And we'll call x of t the number of wolves. So now our population of rabbits cannot just grow forever proportionally to how many there currently are, because there are going to be wolves that eat the rabbits. So how do we model this? Well, let's sort of think about it. What's going on? So when there are more wolves, what should happen? Well, the population of wolves should decline because there's not enough food to go around. If there's too many wolves and not enough rabbits, then the population of wolves will decline. But as long as there's lots of rabbits, then there's opportunity for the wolves to eat, so their population should increase. So this should go up. And it should be proportional to both the number of rabbits and wolves. So as long as there's lots of wolves and lots of rabbits together, then the population of wolves can go up. But also the more wolves there are, the less food there's to go around. So then that makes the population go down. So what is this all saying? Population of wolves, the rate at which it changes, should go down proportional to how many wolves there are. So that's what this part is saying. So this is saying that there's a factor of negative ax, but then it should go up proportional to both amounts. So this is the rate of change of the wolves. And then for rabbits, what happens? If there's more wolves, well, there's got to be less rabbits because they're getting eaten. So the population of rabbits, aka the population of rabbits, should be going down, aka the derivative should be negative here. And then if there's more rabbits, well, they can just breed and make more rabbits. We're assuming that they have an infinite amount of food. So that the more there are, the more they can breed, the more rabbits you get. So the derivative is positive here. So then this is saying that the rate of change of the rabbit population, it's going to be, this is telling us there's a factor of k times y, just like before. But now there's a loss of rabbit population depending on how many wolves and rabbits there are together. So as there's more wolves and more rabbits to be eaten, then the rabbit population will decrease faster. So ky minus cxy. So together we have these two differential equations that model this predator-prey thing. So the idea is that to solve this means determining both x of t, the rabbit population, or was this the wolf population? I forget, and y of t. So we don't have the tools for this one, unfortunately. So we're not going to do this one, but that's the idea. So now let's do another one that we can solve. Also interesting, but I want to give that one because it's different. This one is more spring stuff. We've done so much spring stuff that I don't want to only do those. Okay, but we will do one more spring thing. Coupled springs. It's the next example. So the idea is that instead of just having one spring attached, hanging down like this with one mass, we are going to have a second one sticking out from that one. And then just like before, it's just resting at equilibrium, but now there's two equilibriums. There's two springs and there's two masses. So each mass has its own mass. Each spring is going to have a different spring constant. So I'll just call those K1 and K2 for now. And then we can set it in motion just like before by moving it somehow. But there's going to be lots of different things going on. Okay, so then once it's moving, so let's pretend this blue thing is when it's moving. Well, now we have the position of two different things that we're looking for. So this difference here, we'll call that position 1 because it's the first mass. And this distance here we'll call position 2, away from the second equilibrium of mass 2. So we want to describe P1 and P2 with a differential equation and then solve the differential equation for P1 and P2. And again, we're going to be using forced laws to write these down. Okay, so P1 T is the position of mass 1 from equilibrium 1. P2 of T is position of the other mass, mass 2, from its equilibrium spot, equilibrium 2. So now we're going to write down a dE, actually two dEs, describing the motion by using force laws again. Okay, so let's think about it one mass at a time. Let me draw the picture here again. So the whole point is that the total force equals the sum of the forces. And the total force is ma, m times the acceleration of the mass, which is the second derivative of position. So the total force on mass 1 is going to be mass 1 times the second derivative of its position. Now, what forces are at play here? Well, if it's away from equilibrium, so let's just say that this is equilibrium, and it's down here, we have some restoring forces. So let's just pretend that there's no air resistance right now, no dampening. So there's some restoring forces going on, but from both springs this time. So what's going on is, remember, the restoring force is proportional to and opposite of the wherever the position is. So right now, because it's below equilibrium in this little picture here, there's a force pushing up from spring 1 trying to restore it to equilibrium. And that force is equal to the spring constant, negative of the spring constant, times the position, because it's proportional to the position. So that is always pushing in the opposite direction of motion. So that's why there's a negative there. Okay, so that's one force pushing up on it. Pushing in the opposite direction of motion. So like if the spring was up here, then it would be pushing down because the position would be up. And so that's, again, why there's always a negative, because it's always in the opposite direction of the position. Okay. And what else is going on? Well, now there's this other spring. So this is sort of interesting. So the other spring, what's going on here? Let's see. Gotta make sure I get this right. Okay, so this one is also away from its equilibrium. Maybe it's down here. And so first, this picture is getting all complicated. Okay, so now there's a restoring force for spring 2. So the second spring has spring constant 2, K2. And what you can do is you can think about, in this picture here, mass 1 is below equilibrium, but sorry, I think 1 second. Yes. Okay. Okay. So let me just make the picture less complicated. So now the idea is I'm just looking here. So forget everything else for a second. And this spring has spring constant 2. Sorry, this is still mass 1. So if the mass is down a little bit, if it's squishing this spring down, then once again, there's a restoring force, which would be pushing in the opposite direction of that, based on the position of this first mass. So if this is like equilibrium, but then it's been squished down a little bit like this, then the spring wants to push back up in the opposite direction of the position. The position went down. So the restoring force still does want to go in the opposite direction. So it is still negative, but now it's the second spring and the position of the first mass. I don't know why I keep drawing 2s. This should still be a 1. Okay, so that is a force also on mass 1. So I'm going to add that one. But there is one more, and it comes from mass 2. And so let me draw mass 2. So the idea is that if mass 2 is like away from equilibrium, then there's a restoring force there, which pushes back. So like if the spring is down, like in this situation, below equilibrium, then the restoring force wants to push up. And so again, it's negative K2, position of mass 2 this time, because I'm talking about mass 2. But the interesting part is because it's pushing back up, it's also pushing up on mass 1. So in the opposite direction. So it's hard to draw this stuff. So whenever this restoring force, let's say the restoring force is pushing this way on mass 2, well then it's also pushing this way on mass 1. Hold on, I've confused myself a bit. Had this right before. It needs to be positive on mass 1. What did I think about this before? I guess we could think about it as when it's pushing this up, when the restoring force is pushing up on mass 2, that means that it's pushing up on mass 1. Damn it. Okay, I'm getting confused now. Crap. So it's supposed to be plus K2 P2, but I'm unable to convince myself right now of why that is. So the idea is that the position of spring 2 causes there to be a force on because of the spring 2. And then that force is pushing in the opposite direction of what it's doing for mass 2. So on mass 1, it should be positive, because on mass 2, it's going to be negative. But I've confused myself and everyone watching. So let me just write down the second equation and try to think about this a bit later. Okay, so the point is that this is the differential equation we're looking at for the forces on spring 1. Now the forces on spring 2 will add up to m times acceleration of spring 2. And again, we have restoring forces, but this one's a little bit less complicated. So what's going on is we just have the opposite of these two. So when mass 2 is below equilibrium, like down here, then there's a force in the opposite direction based on mass 2. So it's going to be, and it's on spring 2, so it's negative K2 times the position of P2. And the idea is that that force pushes, it also pushes on mass 1 in the opposite direction. So that's what I was trying to get up there. And then similarly, the restoring force that's pushing in the opposite direction of motion of P of mass 1 based on its position is now pushing in the other direction, so it's the opposite sign on mass 2. Okay, but I've managed to completely confuse everybody. Oops, okay. We got to keep powering through though. So what we want to do now is think about this and read it somewhere else better explained. But what we also want to do is solve these to learn how to solve systems. So that's going to be the main lesson. So forget about all this crap I did. I did a terrible job. Okay. So let's do an example. So let's just suppose that I have a bunch of masses. So mass 1 will be 1, mass 2 will also be 1, K1 will be 6, K2 will be 4. And then these differential equations become, let's see, P1 double prime equals negative 6 P1 minus 4 P1 plus 4 P2. And the other one is P2 double prime equals negative 4 P2 plus, and then K2 is 4 P1. Okay, so how do we actually solve a system of differential equations? Well, we can use Laplace transforms. So we also need some initial conditions. So this would correspond to how you're starting the springs in motion. So let's just say that the first mass started at equilibrium. The derivative, the velocity of the first mass will be 1, so it's going up 1 meter per second to start. The second mass will also be at equilibrium, and its initial velocity will be the opposite direction, be down or up 1. Okay. So now we can use Laplace transforms. What we need to do is, well, we could simplify this a little bit, but after that, we just Laplace transform everything. Then we have a system of 2 algebraic equations that we can solve using algebra and then go back. That's the idea. All right. So let me rewrite these a little bit. P double prime plus 10p1 minus 4p2 equals 0. P2 double prime plus 4p2 minus 4p1 equals 0. So to actually solve a system of differential equations, we Laplace transform. There are lots of other techniques, but this is the one that we can use right now. So we take the Laplace transform of both equations. And it will take a while because it's very big. And it's very hard to keep track of everything as well. But we'll do our best. Okay, so then the Laplace transform. Let's see, the first one. So the second derivative becomes s squared times Laplace transform of the function that we're looking for minus s times the position at time 0 minus the derivative at time 0. The rest I haven't done anything to. Okay, and the second equation, very similar looking, but this is the second position function. So we got to make sure we are clear about that. Oops. And the basic idea is you just do substitution, just like you would in algebra. So you can solve for LP1 or LP2 and plug it into the other equation. So let's simplify one more time. So remember, P prime 1 of 0, that's just 1. But P prime of this guy was -1. And then these are both 0. So that's where our initial conditions will come into play. And now I'm gonna get my LP1s up here. So it's gonna be s squared plus 10 Laplace transform of P1 minus 4 Laplace transform of P2 equals, and I'm gonna add this -1 over because it's -1, so it becomes 1 on the right. And in the second equation, s squared plus 4 LP2 minus 4 L of P1. And this is a -1. So it's 1, and I subtract it over to get -1 there. And these are my two equations. These are two algebraic equations I can solve for LP1 and LP2. So let's do that. Okay, so let me do it the same way I did in my notes because it worked out that time. All right, so let's solve for LP1 on the second equation. So here, what's LP1? So if I subtract this s squared plus 4 over times LP2, and then I divide by -4, these negatives will cancel, which is nice. So let me just make this a 1 and a plus. Okay, and then I'm going to put that back in the other equation. Yeah, it looks horrible. But this will let me solve for LP2. Okay, so I can multiply everything by 4 and distribute this thing in here to get s squared plus 10 times s squared plus s squared minus 10 times s squared plus 4 times L of P2 minus 16 L of P2 equals 4. Now I can subtract this s squared plus 10. And I can factor out this LP2. Four minus s squared minus 10. So far, so good. Oh wait, I multiplied everything by -4. No, I didn't. Preemptively cleared the denominators. Okay, everything's working out, I hope. All right, so now I can divide by this big old thing. So what's that? Negative s squared minus 6 over. So I'm going to distribute this through. So it gets s to the 4th plus 14s squared plus 40 minus 16 on the bottom there. And on top, I'm just going to take out that negative. Down here, what is this? 14s squared plus 24. So luckily the bottom, whoops, I changed that to a 16. That was a 6. Luckily the bottom factors nicely. Plus 12 and s squared plus 2. So then we can use partial fractions to continue. So this will end up being, if you do partial fractions, use Wolfram or something to help you do it quick. Negative 2/5, 1 over s squared plus 2 minus 3/5 times 1 over s squared plus 12 are my two factors. And these are almost like something in the table to do the inverse Laplace transform. They're just missing little square roots. So if I put a square root of 2 here, and then I think of that as square root of 2 squared, now it looks like something in the table. And same thing over here, but with 12. Okay, so it looks like sine of square root blank t. So that tells me, so that was all LP2. So now inverse Laplace transform. And we are almost done. This becomes sine of square root of 2t minus this becomes cosine of square root of 2t. All right, so all that work, and now we have a position function for spring 2. And what else can I do? Okay, so that's position function 2. So I still need position function 1. And what I can do is a system of equations. So I can plug this back in. This is where it's sort of simplified a bit more. So I can plug this in to get LP1. Since I had a formula for LP1, it was this thing. So I'm plugging it in there for LP2 because I just solved for it. All right, so we're going to plug this guy in there up in that formula. So we get 1/4 times, I'm going to bring the 1/4 out to the front, make it look nice, 1 plus s squared plus 4, and this is where LP1 was. So now I'm replacing LP1 with this big thing here. S squared plus 6 over s squared plus 12, s squared plus 2. Okay. And same process. I just got to simplify it and then find the Laplace transform. So let's just keep that 1/4 out there. Let's get this, turn this 1 into s squared plus 12 times s squared plus 2 over itself so that we can combine into one big denominator. Lots of algebra. All right. So then this is the same thing. plus, and now this thing. So it actually simplifies quite a lot. If you FOIL it out, so you FOIL it all out, you'll end up with just, oh, because this is a minus somewhere, I lost a minus. Yes, this was a minus L right here. So this was all a big old minus here, which will make this be minus, which is what we want to happen. So if you FOIL everything out and you simplify, this will just turn into 4s squared up on top there. Now those 1/4 will cancel. Okay, and now we can use partial fraction decomposition to make this look a little bit better, and it'll turn into -1/5 1 over s squared plus 2, and the other one will be 6/5 1 over s squared plus 12. Okay, so now that is LP2. So now I just do the inverse Laplace transform, and it's going to be the same issue. So I need this to have a square root 2, square root 2, and I need this to have a square root 12, square root 12, so that it looks like something in the table. And then it does. Okay, so these are my two position functions. And that's basically it. So we can now find the position of both springs. If you believe my terrible explanation of what the force formulas tell you in the first place. So I got to think about that better and write something up nicer, because I didn't come out right. Okay, but in any case, what you should focus on right now is the process for solving a system, which is you just Laplace both. Of course, this could go on to a system of 3 equations if you wanted to. We're just going to stick with 2. So you Laplace both. Then you solve for L of one of them. I'm just using y1 and y2 in general. Then you inverse Laplace, and that'll get you one of them. And then you also solve for the other. And you inverse again. So that's the process to take away. They take a long time, unfortunately. Okay, so that's it for this lecture. See you next time.